Theme: Design and optical studies of photonic components using slow light properties. Outline: Photonic crystals. We review the fundamental properties of photonic crystals. Slow light. In photonic crystals we concentrate on the basic concepts of slow light. Results and simulation. Discussion of our results. Conclusion:
Future outlook.
Think about it, how has technology changed over the past years? We live in the era of technological world where the latest advancements keep surprising us all. For the past 70 years, semiconductor physics has played a vital role in almost every aspect of modern technology. Advances in this field have allowed scientists to tailor the conducting properties of certain materials and have initiated the transistor revolution in electronics. New research suggests that we may now be able to tailor the properties of light. The key in achieving this goal lies in the use of a new class of materials called photonic crystals. Photonic crystal manipulate light in the same way that semiconductor manipulate electrons. One of the reasons why photonics is the future is that light travels faster than electricity. Light can make devices like computers, mobile phones and medical instruments faster and more energy efficient. There's a big need to make things faster, less energy, smaller and more cheaply. The solution is replacing electrons with photons. Slide 1. Photonic crystals are an engineered optical material represented by natural or artificial structures with periodic modulation of the refractive index, which can prevent light of certain frequencies or wavelengths from propagating in 1, 2, or 3-dimensional. Slide 2. Origin of band gap. A wave incident on a band gap material. The waves partially reflects off each layer of the structure. They combine with the incident wave to produce a standing wave that does not travel through the material. A 2-dimensional and full 3-dimensional band gap material works the same way but in 2 and 3 dimensions. Slide 3. Types of the 2D photonic crystal lattice. There are two commonly used types of the 2-dimensional photonic crystal lattice: hexagonal lattice and square lattice. Slide 4. Electromagnetic wave and periodic structure and block theorem. The field inside a periodic structure takes on the same symmetry and periodicity of that structure according to the block theorem. Periodic function with same periodicity and symmetry of the device. Slide 5. Construction of a band diagram. Construct the band diagram by marching around the perimeter of the irreducible Brillouin zone. We have a band gap here which prohibit the propagation of range of frequencies as we see in picture here. Slide 6. Waveguides and cavities based on electromagnetic band gaps. Using the photonic band gap, PBG, for light manipulation by artificial defects. If light is forbidden to propagate inside a lattice, the lattice acts like a mirror throughout. This can be used to form cavities waveguides. Slide 7. Applications. In recent years, many of the promising applications of 2- and 3-dimensional photonic crystals obtained in the fabrication of high-quality photonic crystal samples, various integrated photonic devices have been realized as. Slide 8. Our subject is slow light in photonic crystals. The incredible speed of light and its non-interaction with the transparent matter has been of great benefit to mankind. It has allowed us to look deeper into our galaxy and universe, and to transmit data over long distances using optical fibers. Why do we need slow light? The first answer, because we can. The second answer is that faster is not always better. Our objective is to design an optical functions based on photonic crystal using the slow light properties and evaluate the potential of nanophotonic crystals. Slide 9. Phase vs group velocity. Phase velocity bold italic v sub bold italic p, speed at which any fixed phase or the shape of the wave is moving. Group velocity bold italic v sub bold italic g, the speed and direction of the envelope of a pulse. Consider two sine waves with different frequencies. Can be written like this. Non-dispersive materials. Slide 10. Dispersive materials. In a dispersive materials, the index of refraction varies slightly with wavelength. Each color will bend at a different angle, causing the colors to separate in different directions. Anytime the refractive index is not constant, the medium is said to have dispersion and the group velocity will deviate from the phase velocity. Slide 11. How do we slow a wave? To slow a wave, we must introduce dispersion. How do we introduce dispersion? Material-induced dispersion. Bose-Einstein condensates. Electromagnetically induced transparency. Coherent population oscillation. Stimulated scattering. Structural induced dispersion. Photonic crystals coupled resonators. Photonic crystals waveguides. Slide 12. Material-induced dispersion. The speed of light in vacuum is extremely fast. Light can travel 30 centimeters in just 1 ns. In 1999 the Danish physicist Line Hou managed to slow down the fastest thing we know, light. She slowed light down to an incredible speed 17 m/s. When atoms get extremely cold, a few millionths of a degree above absolute zero, they lose their individual identities and blend together. At low enough temperatures, a collection of millions of atoms can behave like a single superatom. This collection is known as the Bose-Einstein condensate. The latter has the advantages of room temperature operation, compatibility with semiconductor fabrication technology, the largest bandwidth, and the smallest device size. Slide 13. Structural induced dispersion. Photonic crystal slab waveguide. PC slabs, a high-index material with a two-dimensional array of air holes surrounded by air cladding. The PC waveguide, PCW, consists of a line defect of missing air holes in the PC slab. Light propagates through the defect, confined by the total internal reflection in the vertical direction. Bragg reflection, due to the PBG, in the lateral direction. It has been known since 2001 that the strong dispersion in this waveguide generates slow light in the vicinity of the photonic band edge. Slide 14. The band edge. The band edge is the most obvious place for the slow light phenomenon to occur. Despite this convenience, there are some problems. Dispersion curve near the band edge is typically parabolic rightward arrow strong group velocity dispersion, GVD. Band edge presents a cut-off point rightward arrow propagation mode turns to evanescence mode.
Fabrication tolerance.
So the band edge is not the best operating point. We need the dispersion engineering. Slide 15. The guided modes inside the band gap. We separate the modes inside the PBG by their lateral symmetry of magnetic field to even and odd modes. Even mode is a practical waveguiding mode. The electric field distribution same as single mode waveguide. The frequency hardly change when the propagation constant change means low group velocity. Odd mode. Not a practical waveguiding mode. The electric field distribution is largely different from the signal mode waveguide. Therefore, it is difficult to conduct light. Slide 16. The index-guided and the gap-guided. Index-guided and gap-guide modes. The even mode of such waveguides can be categorized with respect to their field distribution as index-guided mode. Interacts only with the first row of holes adjacent to the defect. Gap-guided mode. Interacts with several rows of holes. If we look at the band edge, we have a shallow slope so there is a low group velocity or high group index. If we move away from the band edge, we enter the slow light regime, the forward and backward traveling components begin to move out of phase but still interact, resulting in a slowly moving interference pattern. As if the mode was making 3 steps forward, 2 steps back. Slide 17. The group velocity dispersion GVD. The operating point is typically parabolic near the band edge. Therefore, slow light tends to coincide with high GVD, which removes most of the advantages of operating in the slow light regime.
High dispersion causes pulse broadening, bit error.
This is not an intrinsic property of the structure, however, but subject to design. We can overcome this limitation by using the dispersion engineering. Slide 18. Some methods for dispersion engineering. There is several examples of dispersion engineering are known, for example, changing the hole size, altering the position of holes, using ellipse hole photonic crystal waveguide, infiltrating fluid into the first row of air holes. Slide 19. Generate slow light regime by shifting holes. Let's see how changing the position of rows of holes can engineer the dispersion curve for produce slow light regime. To understand the dispersion engineering and review the strength and accuracy of RSoft CAD, which is the software using for simulation, we resimulated an important published paper with the follow parameters. Slide 20. RSoft CAD vs MPB MIT. We performed a comparison between our results using a 3D plane wave expansion, PWE, by RSoft software, and the results which use a 3D plane wave expansion, PWE, by the MIT's freely available software MPB. The results are totally equivalent. Slide 21. RSoft CAD vs MPB MIT. Using full wave module, which based on FDTD, the finite difference time domain method, we resimulated a paper published in Nature with more than 1,200 citations. Computed transmission spectrum of the PHC cavity structure, A. Simulation, B. Measured transmission, C. Simulation with full wave RSoft. Slide 22. RSoft CAD vs MPB MIT. By using bandsolve, which based on the plane wave expansion method, PWE, we performed a 2D analysis with an effective index of NEF equals 2.9 to a paper cited by 170 times. Slide 23. The effective index method EIM. Full three-dimensional calculation and simulation of complex devices are very time-consuming and make extreme demands on computer memory. To deal with this drawback, the effective index method, EIM, has been widely used to reduce the actual 3D device to a 2D one. Slide 24. Slow light away from the band edge. The band edge is not the best operating point. First, the dispersion curve near the band edge is typically parabolic, which means that the group velocity changes rapidly with frequency as shown, so an optical pulse with finite bandwidth will disperse over a short distance. Second, the band edge presents a cutoff point, where the mode turns from propagation to evanescence. As a result, the slow mode near the band edge appears to be very lossy. Slow light of the modified photonic crystal waveguide possesses a wide band slow light region where the group index is nearly constant. Slide 25. Slow light applications. Optical switching and buffering. Advanced time domain signal processing. Clock resynchronization. Controlling information through a network. Pulse compression. More sensitive interferometers. Miniaturization. Enhancing linear and nonlinear effects. Slide 26. Slow light applications buffer. Optical buffering. One of the proposed applications of slow light is for the process of optical buffering. Any of the input ports can be dynamically switched to any of the output ports. However, a serious problem can arise if two data packets arrive simultaneously at the switch, because the switch can only deal with one packet at a time. A solution is to build a buffer, which places one of these data packets on hold while the other clears the switch. A controllable slow light medium can perform this function. Slide 27. Geometrically tunable slow light based on a modified photonic crystal waveguide. The first design PCW1. The proposed structure triangular lattice photonic crystal slab consisting of circular air holes. Photonic crystal slab on 3D. The 2D modified photonic crystal waveguide with NEF equals 3.2. Slide 28. Simplest form of a waveguide. Exhibits 2 guided. The linear dispersion curve of the even mode has a wide range of wave vectors, therefore, we discussed only the vertically even transverse electric-like modes. It is clear that the energy is concentrates in the line defect of the waveguide due to symmetric constraint. Slide 29. NG and GVD of W1. As we can see, the group index varies rapidly in the slow light region, so the optical signals propagating through such waveguides will experience a broadening. Slide 30. Guided mode in vicinity of the wavelength 1550 nanometers. The variation of the guided modes versus the radius of the reduced air holes. We observe that the even mode shift towards the higher frequency when the reduced air holes increases. Slide 31. NG and GVD of W1 in the vicinity of 1550 nanometers. It is evident that the group index in the slow light region lies at the wavelength 1550 nanometers area, and as expected the corresponding group velocity dispersion GVD is lower. Slide 32. NG and GVD of the modified waveguide. We have studied the influence of the displacement of air holes position, so we shift the positions of air holes in the second rows on both sides of the line defect. Slide 33. NG and GVD of the modified waveguide. We can clearly see that the slow light of the modified photonic crystal waveguide possesses a wideband slow light region where the group index is nearly constant. Slide 34. The group velocity dispersion GVD. As shown below, the group index curve and the corresponding dispersion group velocity curve of the slow light flat region for the modified PCW are lower than 10 power 5 ps²/km, which is one order of magnitude smaller than the basic photonic crystal waveguide W1. Slide 35. The comparison between our results and previous results. Slide 36. The second design PCW2. Wideband and low dispersion slow light by altering the geometry of a photonic crystal waveguide. We proposed the design of photonic crystal waveguide slab consisting of a silicon core sandwiched by a top cladding layer air and a bottom cladding layer silica. Slide 37. Slow light by enlarging the entire holes. We investigated the effect of the radius of air holes of the photonic crystal waveguide on slow light properties. The bands shift to higher frequencies as the radius value increases. This change is caused by the slab mode band below the propagation mode band. As we see, there is a slow light region corresponding to the radius value r equals 0.4a. Slide 38. Slow light by enlarging the entire holes. We calculate the group index. Also, in order to evaluate the dispersion bandwidth of the slow light, we calculate the NDBP. As r equals 0.4a, group index NG equals 25, bandwidth lambda equals 20 nm and NDBP equals 0.322 has obtained. Considering the compromise between wide bandwidth and high group index of slow light, an essential factor for slow light property is the normalized delay, bandwidth product, NDBP, which can calculated by given formula. Slide 39. Full slow light design. After selecting the radius value r equals 0.4 that produced a slow light, we study the effect of changing the position of the first and second rows on both sides of the line defect in the x-axis direction in order to obtain high group index, NG, low group velocity dispersion, GVD, and high NDBP. Slide 40. Slow light by shifting the first rows. First, we change the position of the first air holes row along the line defect, as we can see the guided modes headed towards high frequencies. The corresponding group index increased as S1 increased. On the contrary, as S1 increased the bandwidth decreased. Slide 41. Slow light by shifting the second rows. Second, we change the position of the second air holes row along the line defect. As we see the guided modes shift towards the higher frequency as S2 increased. We see above the group index, which increases as S2 increases, in contrast the bandwidth decreases as S2 decreases. Slide 42. Dispersion engineering. We tailor the dispersion curve as shown in the right. We have selected two dispersion curves corresponding to the shift values S1 equals S2 equals 0.1063a. We noticed that there is a turning point, A and B, before the curves becomes completely horizontal at the band edge. The turning point A located far away from the band edge, the slope of the dispersion curve, blue, is very small from point A to the band edge. On the contrary, the turning point B very close to the band edge. Using the properties of each curve, blue and red, we obtained an extended curve, green, with a long flat band which provide a high group index and large bandwidth. Slide 43. We selected an optimum values S1 and S2 to tailor the shape of the dispersion curves. As we see, the normalized frequency is a function of the wave vector of the even mode when S1, S2 is varied for optimization. And the calculated group indices is a function of the normalized frequency. We represent in the table below the comparison between our results and the results of previous papers. Slide 44. The group velocity dispersion GVD. The major component of the higher order dispersion is the group velocity dispersion, GVD, is defined by the second order derivative of the dispersion relation. This parameter is very important in slow light devices, because high GVD lead to pulse broadening and signal distortion. It is clearly that the GVD have a low value in the order of 10 power 5 ps²/km. The comparison between the group velocity dispersion, GVD, in this work with the group velocity dispersion, GVD, of previous research. Slide 45. Three-dimensional, 3D, calculation. For a more accurate estimation, we used a three-dimensional calculation. We obtained a TE band gap in the range of 0.31 and 0.48. Only the dispersion region below the light line could confine light well in the vertical direction of the slab, whereas modes above the light line become leaky. Slide 46. We select a supercell by using one air hole along the y-axis, 14 air holes along the x-axis. We recalculated the top three results from the previous table. We obtained the variation of the guided modes by changing S1 and S2 as shown in the figure. Also we get the corresponding group indices as a function of the normalized frequency. The results of three-dimensional and two-dimensional calculation is in good agreement as seen in the table below. Slide 47. In order to demonstrate the results obtained by the PWE method, we use the finite difference time domain, FDTD, method for the proposed structure. For this case, by launch a Gaussian in the center of waveguide with a length between input and output monitor L equals 30A. We observe that the pulse delayed by delta t equals 1.354 ps. We calculated the group velocity using the relation that confirm the value obtained by the PWE calculation. The width of the Gaussian pulse at the output and input monitor is approximately equal, with very little pulse expansion due to the low GVD. Slide 48. We study the optical buffer capability of the second modified PCW, the buffer characterized by the group delay or the storage time increment T expressed as
delta T equals L/VG equals LNG/C.
Buffer capacity cap C. Another important parameter is the buffer capacity C. C equals L/2A*NG delta omega. The physical size of the stored bit. L bit equals L/C equals 2A/NG delta omega. We summarized the slow light parameters and buffer capability of structures in the table below for different group indices. We selected the length of the device L equals 1 mm for better contrasting the buffer capability. Slide 49. The figure in the right shows that the buffer capacity increase when the NDBP increase. The largest storage time is delta T equals 139 ps due to the largest group index NG equals 41.7 but have large bit length also leading to a low capacity C equals 110.9. Thus, the waveguide with shift S1 equals 0.063A, S2 equals 0.1063A have the best buffer capability compared with other waveguides, with a buffer capacity C equals 148.91 and NDBP equals 0.465. Slide 50. As a light pulse enters a photonic crystal waveguide operating in the slow light regime, the pulse length is compressed, resulting in an increased intensity. Slide 51. As we see in this video, we see a wave entering the slow light regime. We notice an enhancement in light intensity. In the second video we observe a wave width of 130 microns. As the wave enters the slow light regime, the wave shrinks and compressed in space, which lead to miniaturization of the device. Slide 52. Buffer working with switch. Slide 53. General conclusion. Studies carried out over the last decade on the use of photonic crystals for the production of integrated circuits meeting the requirements of the new lab-on-chip systems have shown that these periodic structures are potential candidates which can offer new perspectives for the development and production of a future generation of all optical integrated circuits. Optical scientists are turning their attention toward developing useful applications of slow light, including controllable optical delay lines, optical buffers, and true time delay methods. In this work, we explore the design, computation, and analysis of photonic crystals waveguides, and how we slow down the light inside it. The exploitation of slow light phenomena has potential for applications ranging from all optical storage to all optical switching. We review two different types of dispersion-engineered photonic crystal waveguides PCW1 and PCW2 that have been developed for slow light applications such as buffer or sensors. Slide 54. For controlling the velocity of light and slow it down, there are two standard methods. Material-induced dispersion. Structural-induced dispersion. In our work we focused on the structural-induced dispersion. One of the most suitable and attractive structures for realizing the slow light effect is the photonic crystal waveguide, which can have a low group velocity away from the band edge. The basic parameters that characterizes the slow light is the group velocity, g, which is the speed and direction in which the envelope of the wave's amplitude propagates. The group velocity dispersion, GVD, is the second-order dispersion which causing broadening of the pulses when have a high value. The normalized delay bandwidth product NDBP is another important factor for slow light properties. The NDBP is useful when comparing devices of different length or operating at different frequencies. Slide 55. Simulation and modeling using numerical methods running on computers is today one of the key approaches in scientific work within practically all fields of research. Since the physical behavior in the nanoscale is very difficult and expensive to measure in real experiments, numerical simulations play a fundamental role in understanding such processes. We use two methods in our work. The plane wave expansion method, PWE. The plane wave expansion method, which is a frequency domain approach based on the expansion of the fields and material parameters into the Fourier, or reciprocal, space. The components of this expansion represent the definite frequency states. The finite difference time domain method, FDTD. The idea is to simply discretize both in time and space the Maxwell's equations with central difference approximations. We resimulate some important and famous papers published in this domain. We calculated the dispersion diagram and the group index using the PWE method. Also we calculate the transmission of waveguide structure using FDTD method. The results obtained are in a good agreement with the papers mentioned. Slide 56. The objective of our work was to develop a photonic crystal waveguide by introducing a slow light regime with high group index over a broad wavelength range and reducing the unwanted dispersion by engineering the dispersion curve. We proposed two photonic crystal waveguides designs, PCW1 and PCW2. The first design is a triangular lattice photonic crystal slab consisting of circular air holes embedded in a silicon-on insulator, SWA, substrate. We have studied the influence of the displacement of air holes position. We keep the first rows of air holes unchanged and shift the positions of air holes in the second rows on both sides of the line defect in opposite directions toward the center of the waveguide, in order to modify the dispersion curve. The simulation results demonstrate a nearly constant group indices of 21, 20, 35.5, and 65. Their corresponding bandwidths can reach 20.3 nanometers, 15.6 nanometers, 9.5 nanometers, 5.3 nanometers, respectively. We also observed that when the shifting of the second rows of air holes increases, the group index decreases and shifts to higher working wavelength. Besides, the slow light bandwidth become wider. Also, the operational wavelength can be tuned over a wide range span from 1544 to 1574 nm. The proposed design offers great potential for many applications, such as integrated circuits and sensors. Slide 57. The second design is a hexagonal lattice, triangular, of air holes etched in a silicon-on insulator, SWA, substrate. The waveguide is formed by removing the middle row of holes of the triangular lattice photonic crystal in the propagation direction, which create modes propagate along the missing holes confined by total internal reflection in the vertical direction and Bragg reflection, due to the PBG, in the lateral direction. We performed a 2D analysis with an equivalent index of the slab of 2.76 using the effective refractive index method, EIM, because the three-dimensional calculation consuming too much time and computer memory. We studied the properties of this waveguide. We identified a supercell to investigate the effect of the radius of air holes of the photonic crystal waveguide on slow light properties. We observed that the bands shift to higher frequencies as the radius value increases. This change is caused by the slab mode band below the propagation mode band. Also, we explored a flat band, slow light region, corresponding to the radius value r equals 0.4a. Slide 58. After that, by shifting the two rows of holes adjacent to the waveguide in the propagation direction, we observed an inverse proportion between the bandwidth and the group index. Therefore, high group index brings forth slow light but a narrow bandwidth and vice versa. We engineered the dispersion curve to obtain a high group index with wide bandwidth of 18.24, 41.7, 34.55, 33, and 30.43 over 24, 11.7, 16.9, 20.3 and 23.7 nanometers, respectively, which lead us to a high NDBP value of 0.465. For more precision, we used a three-dimensional PWE calculation. We found that the results of three-dimensional and two-dimensional calculation are in good agreement. In addition, to demonstrate the results obtained by the PWE method, we used the finite difference time domain, FDTD, method. The time delay of the pulse in the waveguide delta t equals 1.354 ps, which correspond to a group index equals 28.8 that confirm the value obtained by the PWE calculation. Finally, we proposed an application of our design as a buffer. We calculated the buffer capacity. We have found that for a device with 1 mm length give us 148 bits. Slide 59. Currently, optical buffers require conversion to electrical signals as input to computer buffering and then converting electrical signal to optical signals again. By our design we don't need to convert the optical signal to electrical signal. Also we reduced the size, power, and cost requirements of the buffers needed to perform this operation. Last slide. We have a project. Slow light to enhance the photonic crystals applications. Using slow light to enhance the photonic crystals applications such as sensors, all optical storage, and all optical switching.